So, if you've been following the whole quest for general artificial intelligence, I think the Holy Grail really boils down to one question.
hmm
Can a machine, can it truly reason abstractly? We're not talking about like recognizing cats or just translating text.
So,
We mean learning a brand new, complex, foundational rule from maybe, what, three or four examples?
and then applying it perfectly. That capability, which is, a core feature of our own intelligence,
Mm.
is benchmarked perfectly by the Abstraction and Reasoning Corpus,
ARC.
ARC, exactly. And for anyone who isn't familiar, it's basically a suite of visual puzzles,
Yeah.
little 2D grids of colored pixels.
But the constraints are just brutal.
They are. You get maybe 2 to 4 demonstration pairs,
Right.
input grid and the correct output, and from that you have to figure out a unique rule you've never seen before.
And crucially, solve it for a new, unseen input.
Yeah.
And even though they just look like these simple colored squares, the leading machine learning systems still find this incredibly challenging.
Like an IQ test for algorithms.
Yeah.
It's exactly that.
Yeah.
It tests something we call cross-task generalization,
Mhm.
which is something we humans do effortlessly. But machines struggle because they're so used to learning from massive data sets, by correlation, not from first principles.
So for our deep dive today, our mission is to analyze a new approach that tackles this head on. It's called Vision ARC, or VARC.
And it takes this really dramatic step back from the current language craze in AI.
Right. Instead of turning the puzzle into text, it just treats it for what it is, a visual problem, an image-to-image translation problem.
And here's the kicker, the really stunning part. By refocusing on vision and geometry, VARC achieves performance that actually matches the reported average human accuracy on the benchmark.
It's a huge deal.
It is. It's a compelling challenge to this prevailing idea that you need massive language models for this kind of reasoning. So we're going to dive into the research and pull apart the exact breakthroughs that let a vision model do this.
Okay, so let's unpack the initial setup and, where a lot of the previous attempts maybe went a bit sideways. Before VRC, there's this heavy bias towards making ARC a language or a sequential task.
That's right. So to get formal for a second, an ARC input is just a 2D grid. It can be up to 30 by 30 cells. And each cell just has one of 10 colors. C equals 10, as we say.
Okay.
And then a given task, T, just gives you a couple of these pairs. An input grid, X, and an output grid, Y, that follow some single unique rule.
And the rules can be anything, right? Like find the biggest red shape and reflect it.
Or apply gravity to all the blue pixels.
Yeah.
And when you look at the dominant systems that have been trying to crack this, you see that clear linguistic bias.
The LLMs, large language models.
Exactly. They approach it by converting the whole grid into a text prompt.
So they literally describe the grid in words.
Pretty much. They'll say something like, here's the input. Row 1 is red, red, black, black, and so on. They're relying on all that massive internet-scale pre-training to have, some kind of transferable common sense.
The hope being that somewhere in the trillions of words on the internet, they've learned enough about symmetry or patterns to apply it here.
Right. And then you also have these other models, the recurrent models,
Mm.
things like HRM or TRM.
And they're trained from scratch, but still sort of thinking like a language model.
Exactly. They still perform this iterative, sequential reasoning, step by step, token by token, very much rooted in that 1D flow.
And this is where the VARC researchers had their big realization.
It's the fundamental disconnect. So many of these concepts in ARC reflection, symmetry, rotation, even something like gravity, they are inherently visual. They're physical rules.
We learn them by looking at the world, not by reading about them.
Precisely. So if the rule is apply gravity to blue blocks, trying to parse that through 1D text tokens seems unnecessarily indirect.
You're stripping away the native context of the problem.
You are. You're forcing this spatial geometric puzzle into a sequential linguistic format. VARC just asks a simple question. What if we treat the visual information as primary and let the model figure out its own spatial logic?
Okay, so let's unpack that shift. This move to pure vision. VARC frames this as a classical image-to-image translation problem.
Which is a big pivot, theoretically.
It really is. Instead of trying to find some high-level symbolic rule, they're just treating it like almost like low-level image processing.
Like restoring a blurry photo, or something more high-level like semantic segmentation, where you're trying to categorize every single pixel in an image. The abstraction has to emerge directly from the visual learning process.
So what kind of models are they using for this?
Standard established vision models, things you've heard of, like a vision transformer, a VIT, or a convolutional network like UNet. The key is that the output, the solved grid, is modeled as per pixel classification.
So for every pixel, it's just predicting is this blue, red, green, or one of the other 10 colors.
Exactly.
Okay, but wait a second. If they're using established models like VITs, I mean, those are typically massive and pre-trained on huge data sets like ImageNet, but you said they're training this thing entirely from scratch.
That's the most compelling part. Yes, from scratch. They start with zero knowledge, training exclusively on the ARC grids themselves.
Wow.
And the size comparison is just staggering. The largest single VARC model has only 18 million parameters.
That's tiny.
It's tiny. Most of the LLMs it's compared against are in the billions of parameters.
Yeah.
It just shows you don't need that massive scale. You need the right inductive biases, the right engineering focused on geometry.
But training from scratch on such limited data, there are only 400 training tasks. Right.
Right.
How do you stop an 18 million parameter model from just memorizing everything?
Right.
How do you force it to learn genuine abstraction?
And that leads us directly to the next part. The secret sauce isn't really the architecture itself. The secret is how they engineered visual common sense, these visual priors, directly into the training setup.
So this is where it gets really interesting technically.
Yes. So to stop that simple memorization and force real spatial reasoning, the researchers engineered two key elements. The first one is what they call the canvas.
The canvas. Tell us about that, because they couldn't just feed the raw grid into the model, right?
No. The input grids have all these different sizes, up to 30 by 30. That introduces a lot of complexity. So the solution is every single input grid is placed onto a fixed large canvas. Let's say 64 by 64.
Okay, so it's padded out.
It's padded out with an extra 11th background color. So the model always sees a 64 by 64 image no matter what.
But why does that fundamentally change what the model learns, just having a fixed size?
It's because of how a vision transformer processes its input. It uses patchification.
Right, it breaks the image into little squares.
Exactly, maybe 2 by 2 or 4 by 4 patches. Now, if you just had a tiny grid with no padding, a patch might only ever see one color. It learns nothing, but on the canvas.
Ah, I see. A single 2 by 2 patch can now capture multiple different colors at once, even from a small grid.
Precisely. And if you have 10 colors and 4 pixels in that patch, the model is suddenly forced to consider 10 to the power of 4 possible local color arrangements.
Which is a huge number, so it has to stop thinking about a red dot and start understanding a red dot next to a blue dot that touches a green dot.
It compels the model to learn genuine spatial relationships, local texture. And that's the foundation for all the abstract rules.
Okay, so on top of this canvas, they added augmentations to give it that critical common sense. And I was really surprised by how much impact these had.
They focused on teaching two core principles that we humans just get intuitively: translation invariance and scale invariance.
The translation one, so randomly placing the grid anywhere on that 64 by 64 canvas, that added, what, about 3 accuracy
A
points?
modest 2.9, yeah.
Yeah.
It makes sense. The puzzle should be solvable no matter where it appears on the screen.
But the real game changer was scale augmentation.
That was the big one. This involved randomly resizing the input by an integer ratio, basically, duplicating the pixels to make it bigger before placing it on the canvas. And this one change yielded a massive 6.2 accuracy point gain.
More than double. Why such a dramatic difference?
Because it hits a fundamental blind spot in the vision transformer architecture. A VIT processes inputs at a fixed size.
Right.
So without this augmentation, it might learn something about a red 4x4 square, but it wouldn't inherently know that a red 8x8 square represents the exact same concept, just scaled up.
It's like teaching a kid that a small toy car and a real car are both still a car. The concept is invariant to size.
Exactly that.
Yeah.
And then finally, to really nail the geometry, they used explicit 2D positional embeddings.
Because images are 2D, not a 1D sequence of words.
Right. They use something called separable 2D ropey embeddings. This just makes sure the architecture never loses track of that crucial spatial relationship, that a pixel isn't just token 57, it's column 7, row 8.
So they had the architecture, the canvas, and the geometric common sense from the augmentations. Now, how do they actually train it to do this kind of few-shot learning across 400 really diverse tasks? They use a unique two-stage process.
That's right. Stage 1 is what they call offline training. This is where the model learns all that generalized common sense.
So they train the base model on all 400 training tasks at once.
Jointly, yes. And they amplify the data a lot, using about 1,000 extra generated samples per task from a data set called REHEC. So you end up with about 400,000 samples.
That feels necessary to give an 18 million parameter model enough to chew on. But stage 2 is the real test, test time training, or TTT.
This is the few-shot part. When the model sees a brand new unseen task at test time, the base model is then fine-tuned for about 100 epochs, using only the 2 to 4 examples for that specific new task.
And it's fast.
Very fast, around 70 seconds per task. The idea is the base model has the common sense, and the TTT stage just quickly specializes that common sense to the unique rule of the new task.
And they found something really critical here, right, about how they did this fine-tuning. They found that doing the test time training independently for each task gave much better results.
Substantially better. A massive gain of about 10 accuracy points.
Why would that be? Why is doing them one by one so much more effective?
Well, it really speaks to how complex and unique the ARC rules are. If you try to fine-tune on 5 new tasks at the same time, the model struggles. It's trying to balance 5 unique, often conflicting rules, and it starts to forget the general knowledge it learned offline.
Catastrophic forgetting.
A classic case of it.
Yeah.
By isolating the TTT to one task at a time, you let the model just focus and temporarily adjust its weights to that single rule without breaking everything else.
That's a huge insight. Okay, but ARC is notoriously unforgiving. One wrong pixel and your whole answer is wrong.
Correct. You have to be perfect.
So how do they deal with that?
They use a final engineering trick: multi-view inference. To mitigate the risk of a single mistake, they sample hundreds of different views, 510, in their setup using different augmentations, placing the input on the canvas in slightly different ways.
And then they just take a vote.
Majority voting, yes. This statistical approach helps them find the single most likely correct pixel pattern, but more importantly, it lets them leverage the official ARC metric, which is pass-add-2 accuracy.
Meaning you can submit 2 different answers.
Exactly. Majority voting lets them find the top 2 most popular solutions, which is essential because sometimes the rules are a bit ambiguous. Submitting 2 strong candidates maximizes your final score.
Okay, let's get to the results. What does all this careful vision-centric engineering actually buy them on the leaderboard?
The single 18 million parameter VARC model gets to 54.5% accuracy on the ARC1 benchmark.
And just to put that in perspective,
It dramatically outperforms the earlier recurrent models, like TRM, which is at 44.6%. So it's a clear win for prioritizing visual geometry over sequential processing.
and this small, visually trained model is competitive with systems that are backed by massive LLMs. It's beating some of the early reported scores for things like GPT-5 on this specific benchmark.
All without ever having read the internet.
Incredible. But the headline achievement, the one that really grabbed everyone's attention, came from ensembling.
That's right. By combining multiple VARC models, in this case, one vision transformer and one unit, the performance jumps up significantly.
Bringing the final result to 60.4% accuracy.
60.4.
And that is the critical number because the reported average human performance on the same dataset is 60.2%.
They crossed the threshold. The ARC successfully reached average human capability on this specific, very difficult measure of abstract reasoning.
Purely through a vision-first approach.
It's just proof that baking in that geometric common sense was the right path.
So beyond the raw numbers, did they look under the hood at what the model was actually learning? You know, is it just a fancy lookup table or is it really abstracting concepts?
The evidence points very strongly toward real abstraction. They visualize the internal representations of the 400 training rules, these things called task tokens, using a technique called TSNE.
And what did they see?
They found that the tasks clustered semantically,
Meaning what?
meaning the model was grouping related concepts together on its own. All the tasks that involved coloring a region would cluster together over here, while tasks involving, say, generalized logic operations would cluster way over there.
So it's not just memorizing inputs and outputs, it's learning the relationships between the rules themselves.
Which is the very definition of generalization. And the attention patterns within the VIT were just as revealing.
You could see how it was solving the puzzle visually.
You could. When you visualize which pixels the model is paying attention to, you see this specialization across the layers. Early layers might focus intensely on a tiny core 3x3 pattern, the immediate local rule. But later layers start to specialize in these long-range structures like outward radiating rays that are needed for the final solution. You can actually see the spatial reasoning unfold.
So this deep dive into Vision ARC has really clarified something important for me. That image-to-image translation, when you combine it with the careful, explicit teaching of visual priors like translation and scale invariance,
Hmm.
it's a surprisingly effective and really efficient way to achieve this kind of generalized reasoning, enough to match human averages on a really hard benchmark.
It really provides a necessary perspective shift for AI research. For so long, the approach to ARC was leaning so heavily on symbolic or linguistic methods.
Right.
VARC pulls the focus back to the visual, physical reality of the challenge. It suggests that abstraction and reasoning can, and maybe should, emerge directly from a deep, pixel-level understanding of the world.
So here's a final thought for you to mull over. If an 18 million parameter vision model trained only on small colored grids, just pixels and colors, can achieve human level abstraction by correctly encoding these fundamental properties of our physical world like scale and translation, does that imply that achieving true AGI is maybe less about massive scale language and more about correctly engineering those foundational visual common sense priors? That's something to think about as we move forward in this quest.